1D, solving linear systems. So before we get to systems, let's just graph a line that's in slope-intercept form. So this one is already in this format. So I'm going to need to know the slope and the y-intercept. So here my slope is 2/3 and my y-intercept is -1. So I'm going to start with the y-intercept, -1. So that's where my line crosses the y-axis right there. And then I'll use the slope, which is 2/3, to get to another point from the point I already know. So from that y-intercept, I'm going to go up 2 units and to the right 3 units. So rise over run, right? I went up 2 to the right 3, and then here is my next point, and then I just connect the dots to draw my line, something like that. Okay. All right, so now let's try graphing a system. So a system just means we have more than one equation. So here we have 2 equations. So these ones are not in y equals mx plus b form. You could graph them using the x and y intercepts by plugging in zeros for x and y. That would work fine. I'm going to just rewrite these in y equals mx plus b form. So for this first equation, I'd want to move the 4x to the other side of the equation. Okay, so that I only have y on the left. Now I could write 2 minus 4x, nothing wrong with that, but I'm going to slip the -4x in front of the 2 so that I've got it in a good format here where I have the what's y equals mx plus b, right? So now I can see, okay, for this one the slope is -4 and the y-intercept is 2. Okay, so let's start graphing that one. My y-intercept is 2, there it is. And then for the slope, when it's just a number like this, I still like to think of it as a fraction. So I could write that as 4 over -1 or -4 over +1. I'm doing it this way because I don't have room to go up 4 units. So I'm going to go down 4 units, 1, 2, 3, 4, and to the right 1. And then I've got this line. Okay. So worth noting, negative slope is always going to go downhill if you read it from left to right. Positive slope would go uphill. Okay, next problem. So this one, next equation, I'm going to subtract x from both sides to start isolating the y. Still got the negative in front of the y, don't forget that. And I'm going to slip the -x in front of the 3. And then I want to multiply or divide everything by -1 to change the signs because I want it to say y equals, not negative y equals. So now I've got y equals x minus 3. And now I can see for this one, my slope is 1, or 1 over 1. And then my y-intercept is -3. Okay, so -3 is right there. And then I'll go up 1 to the right 1, up 1 to the right 1. I'll just keep going all the way. And now I've got my line. Now the solution to this system, I graph both those lines. The solution is the point or points that the 2 lines share. So in this case, these 2 lines share this point. So I can see what that point is. It's 1, -2. Okay. When you're graphing systems like this, it helps to graph as many points as you can because if you plot the same point on both lines like I did here, then you know for sure that's the solution. And you could check out that xy pair. That xy pair should satisfy both equations. If you were to get parallel lines, there'd be no solution. And if you got the same line graphed twice, then you'd have infinite solutions because all of the ordered pairs would be shared. Okay, so this system, this method works okay, but only for problems that are kind of set up for it where you get a nice integer solution. It's kind of clunky if you have fractions or decimals or something like that as your solution. Okay, let's try solving a system by substitution. First, what you want to do is isolate one variable in either equation. So you just pick one equation out of the 2 here, or you could even have more than 2 equations, but here we've got 2. And I'm looking at the x's and y's. Well, I've already got the y isolated in the first equation, so I'm going to use that to my advantage. So then step 1 is complete, okay? So now I can see y is equivalent to the quantity x minus 1. So that means in the other equation, what I can do now, where the y is, I can replace it with the quantity x minus 1. So I'm going to rewrite the second equation, x plus the quantity x minus 1 equals 7. So I've substituted into the other equation now. And now I've got an equation with just one variable, so I should be able to solve this for x. So I'm going to combine those x's. This would look the same without parentheses, by the way. X plus x is 2x. Okay, and then I'll add 1 to both sides and divide by 2, and x equals 4. Now it's tempting to just feel like we're finished there because we got x, but we're looking for an xy pair, right? We'd be looking for where these two lines intersect if we graph them. So once you get one of the variables, you go back to one of the original equations. It doesn't matter which one. I'm going to use this first equation, and I'm going to substitute 4 in for x. And now I can solve for y. So y is 3. So the intersection of those two lines would be the point 4, 3. You could write it as an ordered pair if you wanted to, or you could leave it as x equals y equals. They mean the same thing. Okay, so that's the substitution method, probably the most popular method for solving systems. There's also elimination, which is also called the addition or subtraction method, because basically what we're going to do is make a big addition or subtraction problem to cancel out one of the variables. What you want to do first is line up everything. So if you look at the example at the bottom of the screen, the x's, the y's, the equal signs, and the constants are all lined up. So this one I don't have to line them up, but if it wasn't lined up, I'd want to rearrange the equations so that I got the x's and everything else lined up. Okay. Now you want to think about adding or subtracting the equations. I always do this using addition. So if you think about these equations, if we made a big addition problem here, the x's wouldn't eliminate. We'd have 3x. If I added the y's, I'd have negative y. So neither the x's nor the y's are going to eliminate here if I added or subtracted. So I want either the x's or y's to be opposites. Okay. So what I want to do with both of these equations, or at least with one of them, is to multiply it by something so that I can get either the x's or y's to be opposites. Okay, so the bullet point before I start doing that problem, add or subtract equations to eliminate a variable. And then often you will need to multiply one or both equations to make that happen. Okay, so back down to the example that I'm thinking, well, I can either concentrate on the x's or the y's. I think the x's are going to be easier here because you have to do less multiplication, but you could do it either way. So what I'm going to do is take the second equation and multiply everything by -2, because if I do that with the x's, then I'll have 2x and -2x. That's what I want to happen. So I'm just rewriting the top equation as it is. And the bottom equation, I'm multiplying everything by -2. You can't just multiply the x by -2. You got to do the whole equation. So it's really easy to make a little mistake. I think it really helps to keep track of what you're multiplying by as you go, like I did here. Okay, and that way, if you have to trace back you're looking back through your work, you can figure out what happened. It can be really tough to do that if you don't, if you're not organized in the way you're keeping track of your work. Okay. Now, if I imagine this a big addition problem, the x's would add up to nothing, right? 2x plus -2x is 0. For the y's, I'd have -7y, and 3 plus -10 would be -7. So now I have this new equation that only has one variable, and I can solve this pretty quickly. For y would equal 1. Okay. And now I've got one of the variables, and I finish the problem with substitution. So what I want to do now, now that I've solved for one variable, substitute into any equation with x and y. I need to find an equation that has x and y in it. So the original equations are good ones to go to. So I'll use this second equation here. But you could use the first one, and I'm going to substitute in 1 for y. Okay, and then I just subtract 2, and x is going to equal 3. Okay. Now, sometimes some strange things can happen. So sometimes, like on the step when I was doing the addition, the x's and the y's would cancel out at the same time if both of them are opposites. And then it doesn't really tell you what x or y equals, and it seems like it's not going to reveal the answer at all. But those are our special situations where you have either infinite solutions or no solutions. So if you do that and both x's and y's drop out, you might end up with something like this: 7 equals 7. Well, that is a true statement, okay? And if you wind up with a true statement, that means you have infinite solutions. Okay, and if you wind up with something like this, 7 equals 8, well, that's not true. That's false. And if you have a false statement like that, that means you have no solution. So those would be the special circumstances, okay? And that's what these last two bullet points are about. If both variables eliminate and you're left with a true equation, then there are infinite solutions. And no solution if it's a false equation. Okay. All right, so let's try some out on the next page. Let's solve this by elimination. So first thing I would think, well, what if I just added right now? The x's and y's would not eliminate yet. So let me try doubling the first equation, because then I'd have 4x and negative 4x. Okay, so let's see what happens here. If I double everything in the first equation, I get 4x minus 6y equals 6. Second equation, get this, just rewriting it as it is. And now if I add these together, oh, this is one of those scenarios I was just talking about, and actually the constants even eliminate there. But I still have 0, right? Negative 6y plus 6y is 0, and 6 plus negative 6 is 0. So I've got this statement, now I just decide if that's true or false, since there's no x's or y's left. This one is true, therefore I have infinite solutions. In other words, if you graph both these lines, they would actually be the same line, and any xy pair that's on one line would be on the other pair as well, on the other line as well. Okay, let's try another here. If I add these right now, it's not going to work, so I'm just going to decide, am I going to try to eliminate the x's or the y's? It doesn't really matter here. I think I'm going to go for the y's this time just because they're smaller numbers. Also, one of them's positive and one's negative. So that's what I like to circle them just so I don't forget what I was trying to eliminate. Okay, and so if I wanted these to be opposites, I'm going to have to multiply both of these equations by something to make that happen, because I want to use integers here, right? So I'm thinking, what do 3 and 2 both go into? Well, they both go into 6. So if I multiply the top equation by 2, I'll have a negative 6y. And if I multiply the bottom equation by 3, I'll have a positive 6y. Okay, so very carefully, hopefully without making a little mistake here, I'm doubling everything in the first equation, and I'm tripling everything in the second equation. Okay, so I'm just kind of double checking my work here. All right, now when I add these, the y's will eliminate. So I've got 19x equals 19, and hey, I can solve that for x really quickly. X is going to equal 1. Okay, and then I need to go back to one of the original equations. Doesn't matter which one. I'll use the second equation, and I'll plug in that x value here. And now I can solve this for y. So I'm going to subtract 3 from both sides. 2y equals 4, and that means y is 2. Okay, all right, let's try a word problem. Okay, Bilbo has 6 more quarters than dimes for a total of $3.95. How many of each type of coin does he have? Okay, we got quarters and dimes. So I'm going to write 2 different equations here. I'm going to write one equation that has to do with the number of coins. So 6 more quarters than dimes. So let's say he had 10 dimes. That means he'd have 16 quarters, right? So if you, I'll write an equation about the number. So if I take the number of dimes and add 6 to that, that will be, what am I doing here? Sorry, I got ahead of myself. The number of dimes plus 6 is going to equal the number of quarters. Yeah, that makes sense, right? 10 dimes, that would mean I have 16 quarters. So we got more quarters. Okay, and now let's write an equation that has to do with the value of the coins. Okay, so you have to know what a dime and a quarter are worth. So we know dimes, hopefully we know, our dimes are worth 10 cents. So we get 10 cents for every dime, and we've got 25 cents for every quarter. And then we know if we add up the money from our dimes and quarters, we've got a total of $3.95. Okay, so then now we have two equations that have two variables, and we can solve them together. We've got this system that we can solve. We couldn't solve either one of them on their own, but with both of these, we can solve this. So to me, this lends itself nicely to substitution. You could do elimination or even graph these, but I think this is going to be the easiest route. So the q is already isolated in the first equation. Q then is going to be equivalent to d plus 6. So in the other equation, where the q is, I'm going to replace that with the quantity d plus 6. Okay, and now I've got an equation that has just one variable, and I should be able to solve this. So make sure you use parentheses when you substitute, because that will remind you that the next thing to do is distribute. So I'm distributing the 0.25. 0.25 times 6, let's see, 6 quarters would be $1.50. Okay, and then I'll combine these light terms here into 0.35d. Okay, and now I'll subtract 150. Okay, so 135d, and that's going to be 255. $2.45, sorry. I'm glad I checked that. It's early in the morning right now. Not quite on top of my arithmetic right now. Okay, and then I'm going to divide by 0.35. And that should come out to an integer. Here it comes out to exactly 7. So, you know, we'd have a problem with 7.3 dimes. That can't happen, right? So we've got 7 dimes. We still need the number of quarters, but now we can go back and get that pretty quickly. I'm definitely going to use this equation instead of the other one. And we've got 13 quarters then. Okay, 13 quarters, 7 dimes. Okay. All right, and now we get to the good stuff, solving systems with 3 variables. Okay, we got 3 variables here and 3 equations. You can do this with substitution. I'm going to use elimination. So the first thing I do, and this isn't a bullet point, but I would just label all 3 equations. So I'm going to label these equations A, B, and C, just to keep track of things. Okay. Also, you want everything to be lined up like it is here: x's, y's, z's, equal signs, and constants. It doesn't have to be lined up like that, but all 3 equations should be lined up in the same way. Okay. So, first bullet point: pick any two equations and eliminate one variable. Okay. So it doesn't matter which one you eliminate. I'll just go for the x's here. So just to remind myself what I'm trying to eliminate, I'm going to do this, because I'm going to have to eliminate the same variable twice, okay? But I'm picking any 2, so let's just do equations A and B to start with. So I'm thinking, all right, eliminating x's, I'd want to double equation A. So I like to keep track of it like that. For these problems, I think it really helps to put a little line through your z's so that they don't look like 2's. It gets confusing if you don't do that. Okay, and equation B, I'm just copying it as it is. Okay, oh, and in the first equation, I forgot to double the 7 there. This should have been 14, because I was talking and writing at the same time. Oops. Well, that's what I'll blame it on anyway. Okay, so now let me double check. Yeah, the first equation's all doubled now. All right, so now when I add these together, those will eliminate, and I'll get 5y plus 5z equals 15. Okay, so now I've got this new equation that only has 2 variables. I'm going to give it a name. I think I'll call it equation D. Okay. Next bullet point, I'm going to pick 2 different equations and eliminate the same variable. Okay, so I used A and B in the last round, so I don't want to use A and B again. I could use A and C, or I could use B and C. I'm going to choose A and C. It just looks a little easier to me. Okay, and I'm eliminating the x's, so let's see. If I multiplied equation A by -3, then I'd have 3x and -3x. That's what I want. Okay, so multiplying everything by -3 in equation A. Okay, everything's multiplied by -3. Just double checking that. It's so easy to make little mistakes on these, and it's really hard to tell if you made a mistake until the very end when you get a weird answer. The problems I assign always have nice integer answers, so that's a hint if you get a fraction or a decimal answer that something is wrong. Okay, so let's see. I'm now adding those equations, and I'll get -7y minus 5z equals -17. Okay, so let's call this equation E. All right. So now I've taken the 3 equations with 3 variables, and I've boiled it down to these 2 new equations that only have 2 variables. So that's kind of phase 1 that I just completed. Now I'm going to take equations D and E, and I'm going to think of that as a new system. So I'm looking at those and thinking, well, if I just added them right now, would anything eliminate? And I lucked out here because the z's are already opposites. Okay, so a lot of times you'd have to do some multiplication first. So here, I'm using elimination to solve these. You could actually use substitution if you preferred at this point. Okay, but yeah, I'm using elimination here. So now let's see, -2y equals -2, and that means y is going to equal 1. Okay, now I'm solving this system here. So we've got the y, but this system with with 2 variables and 2 equations still has a z, right? So we want to go back and get the z as well. All right, so I'm going to go to either equation D or E. It doesn't matter which one. I think I'll use equation D, and I'll just plug in 1 for y. Okay, and then so 5 plus 5z equals 15. Now I can subtract 5 from both sides and divide by 5, and z is going to equal 2. Okay, once you get 2 of the 3 variables like we have here, you want to substitute them into one of the original equations. It has to be one of the equations that has all 3 variables. Okay, so it doesn't matter which one, I'm going to use equation A. So let me zoom out so I can see that again. -x plus y plus 2z equals 7. Okay, and I'll plug in what I already know into this. I don't have the x yet, but I have the other 2 bits. So the y was 1, and the z was 2. Okay, so that'd be 1 plus 4, that gives me 5. Now I'll subtract 5 from both sides. And then divide by -1. And I've got, whoops, I was dividing by -1. So x is -2. Okay, and I've got x, y, and z. You could leave your answer like it is here. You could also write this as an ordered triple. So you make sure you want to go alphabetical for an x, y, z pair, or triple, I should say, like that. Okay, so that is equivalent. Okay, those ones take a while. So be really careful with your work and keep track of what you're doing. All right, that's the end of the section, and I'll see you next time.